morning and welcome everybody to my presentation. The title of my talk today and of my research project is Design and Optimization of Front-End Circuits for Ultra-Low Power Energy Sources. My tutor is Professor Bertacchini and my co-tutor is Professor Larker. The target of my research activity is design of high-efficiency power conversion circuit for energy harvesting and wireless remote powering application. And here are some examples of my research project I worked on during my PhD. And in particular, I worked both on the realization of power conversion circuit on integrated circuit technology and both on PCB technology. This kind of circuit find application in the mainly in wireless sensor networks. Wireless sensor networks are specially distributed autonomous sensors that monitor some physical or environmental condition. And these wireless sensor networks find application in several application fields, like medical field, logistic and industrial field, monitoring of building like bridge in this case, agricultural field and so on. And one of the bottleneck in the development of wireless sensor network is the supply of the remote nodes, because nowadays solutions exploit batteries, but batteries have high cost of implementation and maintenance, especially due to the fact that processing power doubles every 2 years, while the battery capacity doubles every 10 years. So it is necessary to try to extend battery lifetime and possibly to completely replace battery. And to do this, it is necessary to exploit the energy present in the environment. And so we talk about energy harvesting. The design challenges to develop energy harvesting system are listed here, and first of all are the design of efficient transduction devices that transduce the sources present in the environment, like sunlight, thermal energy, vibration, or the energy associated with the electromagnetic wave at a radio frequency. It is also necessary to reduce the power consumption of the nodes, of the remote nodes. And in particular, it is necessary to modulate the power consumption of the nodes, also dependent on the power and the energy available during the time. And finally, it's necessary to develop high-efficiency, low-power management circuit. And my PhD project focused mainly on this third point. In this research project, I mainly worked on these activities, where my main activity research was the design of RF to DC converter for RF energy harvesting and power delivering. And then I also worked on these three-side activity, in particular the design of a PCB power management circuit to efficiently combine the RF harvester implemented in IC technology with a commercial battery, the design of a step-up DC-DC converter in PCB for direct methanol microfuel cell, and finally the design of AC to DC power converter for vibrational energy harvesting. So I start with the description of my main research activity. The idea of harvesting and power delivering is to collect the energy associated with the electromagnetic waves at the radio frequency. And we talk about harvesting if we exploit the waves present in the environment, while we talk about power delivering if we have an ad hoc source. The main difference between these two systems is the operative frequency, because for harvesting it is necessary to develop converters operating in a wide band of frequency, while for power delivering we have to work with system with a narrow band of or single frequency. And nowadays IC technologies does not allow to implement efficient RF to DC converter for energy harvesting, because the wide frequency range is a very strong limit. And for this reason, I developed RF to DC converters for devices to operate with an ad hoc source, so for power delivering. And in this research project, I worked on the design of and the realization of two IC prototypes, both operating at 868 MHz, both realized in ST139 nanometer CMOS technology, but one realized to convert the energy provided by a single-ended antenna, the second one realized to work with a differential antenna. For both this kind of system, the main design constraints are listed here, and in particular, the very low energy and power available at far-end location, and the unpredictable variation of the available power. That depends on several factors, like the distance between the source and the node, the transmission channel condition, the antenna orientation, and so on. So, first of all, it is necessary to maximize the conversion efficiency over a wide input power range of available RF input power. And for this reason, a reconfigurable RF to DC converter has been developed. Besides, from the application point of view, it is necessary to regulate the supply voltage provided to the application, and without wasting the low energy available. And for this second objective, a smart voltage regulator has been developed. This is the block diagram of the single-ended RF to DC converter, comprised of the antenna, that is a standard 50 ohm antenna, the matching network that has to maximize the power transfer between antenna and the rest of the chain, the reconfigurable voltage rectifier that transforms the RF signal into a DC voltage, and the smart voltage regulator that maintains constant the output voltage of the rectifier by charging an off-chip capacitor. And I start now to describe more in detail the implementation of such blocks. In particular, I start with the core of the wall converter, which is the reconfigurable voltage rectifier, which is comprised of two basic blocks that can be connected in series or in parallel through MOSFET switch, highlighted here in red, MA, MB, and MC. And each basic block is a two-stages voltage rectifier. And so, connecting in series or in parallel the two blocks, it's possible to obtain a full 4 stages or 2 stages Dixon voltage multiplier. And the output voltage of the wall converter is shown here, is twice the number of stages of the full voltage rectifier multiplied for the amplitude of the RF signal minus the maximum gate source voltage lost on each diode connected MOS transistor. The output voltage of the rectifier is maintained constant by the smart voltage regulator, that is a very simple circuit that resembles a current mirror. The operating principle is the following. Transistor MF2, MF3 fixes the MF1 gate voltage. And if the available power tries to increase, also the source to gate voltage of MF1 tries to increase too. But this raises the source to gate voltage of MF1, and supposing MF1 operating in saturation, this raises the DC output current drained by MF1. And so this lowers the DC resistance C at the Vout side, and this so lowers also Vout, and counteracting at the initial output voltage variation. The DC output current is proportional to the available power, and so the higher is the available power, the faster is the charge of the capacitor. Finally, the third block is the matching network that has to transform the input impedance of the rectifier into the antenna impedance. That is a standard 50 ohm antenna. The input impedance of the rectifier is the parallel of an input capacitance and input resistance, both calculated in stationary periodic conditions. And the matching network topology is based on a P topology, because this topology exploits constructively the parasitic introduced by PET capacitance and parasitic bonding inductance. The efficiency of the matching network is shown here, and is given by a nomic term related to the parasitic resistance introduced by bond wire and the external matching inductor, and a second term related to mismatch, in particular the power that does not go into the matching network but is reflected, and this is taken into account through the reflection coefficient S11. So the input resistance, as shown in the graph, varies with the DC output current of the rectifier. And let me remember that the output current of the rectifier is proportional to the available power. So the input resistance varies with the available power. And this is also demonstrated with this simplified formula for the input resistance. And so the smart voltage regulator that maintains constant the output voltage modulating the E out determines the variation of the input resistance. But the variation of the input resistance also determines any variation of the matching network efficiency. And this, in particular, we have an optimum matching efficiency at a given input resistance value, and moving away from this optimum input resistance determines the degradation of the matching network efficiency. And this also limits the input power range in which the whole converter works efficiently. To overcome this issue, we devised the reconfigurable solution for the voltage rectifier. So changing the number of stages of the voltage rectifier also changes the dependency of the input resistance with the DC output current. And so this increases the input power range in which the converter works efficiently. This is also allowed by the fact that the input capacitance does not depend on the number of stages, but depends on the total number of transistors composing the rectifier. And this total number of transistors does not change, changing the total number of stages. This is the microphotograph of the realized IC prototype. And the measurement setup comprised of the network analyzer that emulates the 50 ohm antenna and measures the reflection coefficient at the matching network input. The matching network is implemented on an ad hoc PCB, and this is the efficiency measurement of the converter. It's worth to note that efficiency peaks at 60%. That is a very good result with the sensitivity, and so the minimum RF power for which the converter turns on, of -17 dBm. But the very great result is that the efficiency remains above the 40% for an input power range of 14 dB, thanks to a reconfigurable solution for the voltage rectifier. Here, the output voltage of the voltage rectifier that is maintained constant at 2 volts from the smart voltage regulator, and the measured reflection coefficient at the antenna, so at the network analyzer. And the two peaks demonstrates once again the two perfect matching conditions at two different available RF input power. This second block diagram describes the differential RF to DC converter, which is similar to the single-ended one, but with two main differences. The first one is the RF to DC converter that must be with a differential topology. And the second one is the matching network that in this case is not present because it is designed this circuit to work assembled with a custom PCB antenna. And the differential voltage rectifier is again based on a configurable solution, and the implementation, transistor level implementation of the basic block is shown here. And in particular, the cross connection scheme shown here highlighted in red allows to reduce both power losses introduced by the on resistance and the threshold voltage of transistor when the transistors are on, while also the off power losses due to leakage current with respect of the classical diode connected transistor. And these are the results obtained on the second prototypes. The results are plotted both for the characterization setup with a 50 ohm antenna, because the instrumentation is single-ended at 50 ohm, so we developed the PCB that implements a balloon and the matching network, and then the results were embedded to obtain the efficiency expected for the customized antenna. The efficiency, again, peaks at 60% for the customized antenna solution, but with a sensitivity of -21 dBm and with the efficiency higher than 40% for an input power range of 20 dB. The performances of the solution implemented are compared with previous artwork, and it's worth to note that the peak efficiency is the higher one, and nevertheless, the circuit are implemented in standard CMOS technology. In such case, other solution implements in literature implements some CMOS option like floating gate or Schottky diodes, and the sensitivity is comparable to the other work in literature. I finished spending 2 words about the other 3 side activity I worked on during my PhD. In particular, the design of a power combining circuit that combines the energy provided by one of the 2 RF to DC converter implemented with the energy provided by a battery, a commercial battery. And the circuit is basically based on switching topology. And the basic principle is that the power combination is done at the VBAT node, combining the current provided by the RF harvester and the current provided by the battery. Secondly, the design of a step-up DC-DC converter for direct method on micro full cell, and in particular to up-convert the low input voltage provided by the micro full cell, around 300 millivolt, to supply voltage able to supply the application around 3 volts. And finally, the design of an AC to DC converter for vibrational energy harvesting application. The system is comprised of a piezoelectric transducer that transforms the vibrational energy into an electrical signal. Then the AC to DC converter converts the sinusoidal electrical signal provided by the transducer into DC voltage and charges a capacitor. And then the energy stored into the capacitor is then managed by a power supply management circuit. These are my publications I've done during my PhD, and thank you for the attention.
Thank you very much for your presentation. In the case of the piezoelectric system, which applications are you thinking about?
This system were implemented for a safety in agricultural application. So to mount on, I don't know the right term in English, but to mount on implements. On sensor on implements for safety. And this is under a regional project done during my PhD.
Okay. So in the other case in which you have a source plus a battery, you try to combine the currents coming from both sources, yes, so that when for instance, it's not a sunny day, the battery provides most of the power and...
yes, sir. I think you mean here.
Yeah, yes, this one.
Yes, if there is no RF power, all the energy is provided by the battery. Indeed, okay, if the power is enough of, well, the power generated by the RF to DC converter, the battery does not provide any current.
Okay. Oh, the problem, for instance, of converting a very low voltage to a voltage, an higher voltage, DC voltage. It's another interesting problem. It's a very good talk. Thank you very much.
Thank you.
So we have, unluckily, we have the last candidate of this morning, Mr. Luca Vandelli.
Yes.